and then you're good to have your. I'm sorry, I'll keep playing.
No, it's okay.
I'll take it out. Hey, y'all, we're gonna go ahead and get started in. In your future experiences. But before we do get started, I'm going to go over some following information. If you're new to ACM, go ahead and scan this QR code. By scanning this QR code, you will be eligible for free swag, giveaways, and internship opportunities. Keep in mind that membership is absolutely free this semester, so you don't have to worry about anything. And do notice that some people are scanning the QR code, so I'm going to let it run through a little bit. But for everyone who is a member, go ahead and scan this QR code. By scanning this QR code, we will be able to keep a tally on the events that y'all are attending. And keep in mind that by attending 15% of our meetings or 7 meetings this semester, you will be eligible for a free ACM t-shirt along for a giveaway that we will have at the end of the semester brought to you by ACM. But as y'all are scanning those QR codes, I will be going over some of the events. On December the 2nd, we will be having a holiday social. This will be only an in-person event that we will have here. So if you want some hot chocolate and want to play some games before the start of finals, I highly encourage y'all to come. In addition, ACM has partnered with Adoptive Family, and we will be receiving some gifts for us to wrap. And by wrapping these gifts, we'll be giving them away, or we will be giving them to families in need. So if you're looking to make someone's holiday season truly special, I highly encourage y'all to come and help us wrap some gifts while also enjoying some hot chocolate and games. And for more information on this, please make sure to look at our ACM-W Instagram page. But aside from this, these are your weekly opportunities for this week. For this weekend, ICPC will be meeting at the SEB Makerspace and virtually. So if you're interested in nailing your technical interviews, if you're interested in learning more about competitive coding and attain new experiences, this organization is a great way to get started to help you nail some technical interviews and boost up your coding experience. But aside from this, we also have Code Quantum. So last semester, we had a very successful hackathon, and this was done through the help of our organizers. And because of our organizers, we were able to produce an amazing hackathon for the city of San Antonio. So Code Quantum is a hackathon for underrepresented genders and minorities, or underrepresented genders. If you would like to help join the team and create the second iteration of Code Quantum, go ahead and scan this QR code. And by scanning this QR code, you will be an organizer to help, and that will be able to help create a gender equality and inclusive environment. Just as a reminder, you do not have to be a gender minority or a minority student to become a team member. As long as you're willing to help out the community, we're more than happy to have you. But now, without further ado, I'm going to go ahead and let Janelle Millicent come to the front of the stage, where she will be talking about computer vision. So go ahead and give her a warm round of applause.
Okay. Can y'all hear me okay? All right. Perfect. So first of all, I just want to say thank you so much for having me. And I'm really excited to talk about computer vision because that was something that started my career in CS, and like that was actually the topic of my first internship. So it's pretty near and dear to my heart. And so I hope to provide a similar experience for you all to maybe learn something you like, or at least learn something you're not interested in and narrow it down. So without further ado, what we're going to be talking about today is first we'll go over what is computer vision. Then we'll talk about OpenCV, which is a library that gives you a bunch of functions to perform computer vision tasks. Then we're going to talk about how computers see images so we know how to use these functions. And we're going to go into depth with two of our functions, such as thresholding and finding contours. Then we'll define our problem, which is shape detection. Then we'll do a demo. So I have this tiny URL up here. So go ahead, and if you have your computer and you want to follow along, please go to this link now and you'll see a Google Colab document. And the reason that this is going to be really good for us is you don't need to install anything, you don't need to download anything that you type in that's the same as what I type in will give you working code at the end of this. And that's what I'm really shooting for, is that all of you have some sort of project towards the end of this that you can either go back to or extend if you have the time. Oh, it's locked. Okay. Let me fix that really quick. Okay, so instead, I'm going to drop a link in Discord. So if you all are not already in the Discord, now is a perfect time to join. You can go to discord.acmutsa.org. All right, and I'll just put it in the general channel, and you all can tell me if that one works for you. Hopefully it does. If not, there's no code on here, there's just text. So, all right, cool. So now that we have that squared away, we can go ahead and get into our presentation. After the demo, I'm going to wrap up with what you can do next with computer vision or this project in general. All right, so first, what is computer vision? So this is a definition from IBM, and I'll let you all read this, but basically what I want you to get from this is computer vision is the study of trying to get computers to see and understand information. So they can see information in the form of videos, in the form of images. Videos really is just a sequence of images. And so this is what will allow us to get information from those images, and then we can understand things like what shape is there or what color is there and things like that. So a subfield of computer vision is image processing. And this is what people who are familiar with computer vision usually do first. So for instance, you can denoise an image. So if you've ever seen an image and it looks like super grainy, or maybe it has that like radio static on it, that can be noise, but noise can also be in a less obvious form. There's also super resolution. So if you have a blurry image, you can use image processing to go ahead and sharpen all of the edges in the image and make it look clearer. You can also do color thresholding, so you can see what colors are present in certain parts of the image or even detect and localize colors. And the main purpose of image processing is to enhance images and then also prepare images for other tasks, like if you want to feed the image into some sort of machine learning or deep learning model. So more on computer vision. So we talked about a subset, which is image processing, but the broader scope of computer vision, there are, at least in my book, about 5 like main tasks, and you might see this different from whoever you ask, but in my book, they're image classification. So if you have an image of a cat, you can classify whether that image is a cat or a dog's or something like that. And then you can also do object detection, which is very similar, which would be like, one is the case that a cat exists in the image, and 0 is the case that it does not. You can also do object localization, which is shown in this picture that my mouse is over, where it actually draws a bounding box around the object. And then the last 2 are segmentation tasks. So the first is instance segmentation, which is the picture on the far right, which is not only interested in what's in the image, but separating out those from multiples of each other, right? So we see that there's 2 dogs in this image and both of them are labeled. Whereas in semantic segmentation, you're only concerned with what is a dog. You're not concerned if one dog ends here in the picture and one dog ends at another part in the picture. You're only concerned with classifying all the dogs as a certain color. And that's represented by the picture on the left. So now that we've defined a little bit about computer vision, we're going to talk about OpenCV, because OpenCV is a great tool for if you're interested in computer vision, because you don't have to type out all of these functions or all of these attributes. They're already in the library for you. And so OpenCV is commonly used in Python. If you want to look at the documentation, I would just Google OpenCV Python documentation. And that's how I put together this presentation, or really any project, is I just go to the documentation and I look at what's out there, because you never know the functions that you can use until you look at the documentation. But I'll show you a couple functions that I picked out. All right, so now that we know that we have a tool that can help us with computer vision tasks, we need to know how our computers are seeing images. So if you've ever heard of an image that's like 256 by 256 or 64 by 64, that is referring to the pixel width and length. And so you see here, this is an example that's pretty pixelated, just to illustrate a point. Usually those pixels would be a lot smaller, and so you would get a lot clearer of an image. But you can see that this is a grayscale image of some face. And since it's grayscale, each pixel is going to have one value on the scale of usually 0 to 255, 0 being black and 255 being white. And so how our computer actually sees this is as a two-dimensional array or a matrix of these different values of the pixels. So that's what's shown on the right is just how our computer is seeing those images. Now, there's not only grayscale images, there are also colored images as well. So how do we represent those? Well, it's the same thing, except for instead of just having one value per pixel, you'll have what's known as a tuple, or you can just think of it as a list of 3 different values. And so, for instance, we know that red, green, and blue are color values that can make up all of the spectrum of colors. And so you can also use this to describe pixel values, except for we have to be careful because OpenCV, when it's describing pixel values, uses BGR. It does not use the order red, green, blue. It uses the order blue, green, red. And I see that you look a little bit annoyed by that, and that is a fair assessment. It is a little bit annoying. It'll catch you a couple times. But there's also one other way to represent pixel values, and that's by 3 different values called hue, saturation, and value. And so I added a little diagram here where you can see as like the hue changes or the saturation changes. So for instance, saturation makes the color less white and more true to its color. And I don't really want to focus or spend too much time on this because for today's demo, we'll just be working in grayscale mainly. All right, so now that we know a little bit how a computer sees images, we're going to go ahead and dive into some of these OpenCV functions. So the first one that I want to point out is thresholding. So what is a threshold, or what is thresholding? Thresholding is when you tell the computer, hey, if this pixel is above or below like a certain value, I want to set it to an extreme value. And the reason why we want to do this is because for things like detecting edges or detecting different colors, it's less likely to mess up if we're finding an edge between, let's say, black, so 0, and 255, which is white. There's not much room for error there. Whereas if we have a color that's in between, where it's 2 gray values, and we're trying to detect an edge between 80 and 100, then maybe our detection isn't going to work because it's not an extreme difference. So that's why you would want to threshold an image. And in particular here, we're going to threshold it so that we can see the lines that make up the shapes. So like I said, thresholding is if a pixel value is lower than a threshold, then you want to set it to your maximum value. And if it's higher or otherwise, you want to set it to 0. And so this function here is from the OpenCV library. It takes an image, and then it takes your threshold, and then your maximum value, and then the threshold type, which we will get into in the next slides. And it returns 2 things, but the most important thing is the thresholded image. That's what we want to capture. So these are the threshold types. There's a lot of them. This is found in the OpenCV documentation. So if you want to go look, feel free to, but the ones that I want to point your attention to are the thresh binary and the binary inverse, which are the 2 top ones, because these will do mainly what we want them to do. So for the binary, if the source, so that's our image at X and Y, those are our pixel coordinates. If that pixel is greater than the threshold, we'll set it to the maximum value. And if not, we'll set it to 0. So we'll end up with a black and white image. And then the one right below it, thresh binary inverse, is the same thing, but flipped, so inverse. So we are looking for pixels that are less than the threshold to set to the maximum value. So that's kind of how thresholding works. Does anybody have any questions on that? And we'll go into a bit more detail, but I want to give time for any questions if you have any. Okay. Well, so this is an image on the left is our original image, and then the image on the right is our thresholded image. So we can see that now going from all of these different colors where it might be hard to detect whether that red, because it's a little bit darker, is black or red, we clearly have white shapes and a black background. So it's going to be really easy to detect the contours that make up the shapes. And so contours is actually the next part that we are going to focus on. So a contour is just a curve that is joining the points along a line. So it doesn't have to be straight, it can be curved. But you can just think of a contour as an edge. So anywhere in a picture, like the square right here, anywhere there's an edge, that green line represents a contour that's fit to that edge. And so OpenCV has a function to find contours on an image. And so when we give it the thresholded image, it'll be able to find all of the areas where there's a significant difference from one pixel value to the next, and it will flag that as an edge or a contour. And so for this function, we just need to input the image, the retrieval mode, and the approximation method. And those two things I will get to in the upcoming slides. But the output is going to be a list of our contours, and then a list representing the hierarchy of contours. So for instance, in this image, the contour that's inside the square would be a child of the contour that is on the outside of the square. So that's what we mean by hierarchy, is it gives a little bit of information of how these contours are arranged. So I mentioned that we need two arguments, the first of which is the retrieval mode. So this answers the question, what contours are we getting? How are we getting them? So OpenCV has methods that are already defined for you that you just have to call exactly what I have typed on here, like CV underscore RETR external. And if you call that, what it will do is it will only get the extreme outer contours. If you call the list, it will get all of the contours, but there won't be any hierarchy. So if you don't need to know what's inside of what or anything like that, that's definitely the one you want to use. We have another one that returns a hierarchy, but only on two levels. So it's either a container or a hole in that container. And then the last one will return all of the contours with the full hierarchy. And so I have a little visualization, because I know contours, that's a bit difficult to understand. So I was talking about how contours can be a child of a different contour or a parent of a different contour. So how the output will look when you print what the hierarchy is it'll be 4 numbers for every line. It'll be what's the next contour, what was the previous contour, what's the child, and then what's the parent. So if we have these shapes and we go here and we just return the external contours, we can see that on the right, there are some, like this square has a value of 2 here. I know it's a little bit small, so it's referring to the, let's see if that was a parent or the child. It's referring to its child is 2. And we look at 2, and 2 is this inner contour. So it is able to display that parent-child relationship there. Any questions on contours? Okay. Well, so the second part of our contour function is going to be how we approximate our contours. So there are 2 different methods, and one is where we save every single point in that contour, and that can get pretty memory intensive. So if you think of a image that's 1,000 pixels by 1,000 pixels, and it's just a rectangle, but the rectangle goes across the whole image, then you'll have about 1,000 times 4 different points that are saved. And so that can get kind of intensive. And so that's what is referring to the chain approx none. It will save every single pixel value on your contour. But what we can do is we can use the method that is the chain approx simple. And this will only save the points that are at the different edges of the contours. And so the illustration of these 2 are here, where the chain approx none is on the left, where you can see it saves the entire line. In red is what it saves. But on the right, you can see that the simple method just saves the 4 points. So we're saving a lot of memory. We're getting rid of a lot of information that's not going to be useful to us down the road. So I would recommend that you use the simple one, almost always. All right. So I want to recap what we've learned, and I've allotted a lot of time for this demo because I want you all to like stop me and ask questions, or if your code doesn't work, like let me know, because my goal is to have everybody come out of here with working code. So I want this to be like pretty interactive. But before we go on to that, I wanted to recap that we learned what computer vision is. It's how, or the study of how computers can see and understand information. We also learned what OpenCV is. It's a library, or as it's known in Python, a module, where it has a bunch of functions and different attributes and things that we can use to help us with computer vision tasks. And then we also learned how computers see images as matrices of pixel values, where these pixel values can either be one value per pixel, where it's grayscale, or it can be a tuple of values or a list of values where it's red, green, and blue, or in OpenCV, blue, green, red. We also learned about what thresholding is, where we set that extreme. And we also learned what a contour is, where it's an edge, and we can detect them using this chain approx simple method, where we don't have to save all the points on the edge. We can just save the most important ones. So now's the fun part, where we're going to get into a demo. So our problem for this demo is going to be shape detection. So first of all, what does that mean? That means, how do we determine what shape we have in an image based on the contours? So what we're going to do is we're going to use the contours to estimate the main points in the shape. And then from these main points, we'll be able to tell how many sides are in the shape. Because you think about a triangle, it has 3 main points, right? Well, if it has 3 main points, then we can say it's a triangle. So we can code that and use that to detect and label different shapes in an image. And so I mentioned that we're going to use our contours to estimate the number of important points. And that is executed by this function, which is also in OpenCV, and it's approx poly dp. So it takes as input a curve. So that's going to be our contour. And then the second argument is epsilon, which sounds a little bit daunting, but this is just a measure of how much error we're okay with in our approximation. How far can our approximation go from the contour? So that's just a regularization term for us. And then the last one is closed, where it'll be a Boolean value. So either true or false, as in our shape is closed, meaning that it's a full triangle, or if it was just a single line, then it would be open. So closed would be false. And yeah, so the output of this function is a list containing the approximation of the important points as x and y values. And so we don't even need to know the x and y values. We just need to know the length of the list, or how many points are important, because then that'll tell us how many points we have, and therefore how many sides in our shape that we have. All right, don't go to that link. Go to the link in Discord. It's in the general channel for anybody who doesn't already have it up. So you should be seeing this collab notebook. And like I said, you don't need to do anything. Everything's already pre-installed, so we can get ready to code. But for anybody who hasn't used Google Colab before, I want to give you a little bit of a tour, or show you how to work with this notebook a little bit. So you'll see in the upper left-hand corner that there's a button for plus code and plus text. So code is going to give us a block of code, and text is going to give us a block of text. So right now, all that's in here is text. I was mean, I'd give us any code. We're gonna have to code it all from scratch. So all I gave us was text with instructions. So we can click on this first block. And actually, everybody, I think you only have permission to view this notebook. At least I hope that's right. So go to File and save a copy in Drive, and save your own copy so that you can make all of your own changes. But don't worry, this is all shared with you, so you can still view it. So if you get behind or anything like that, you need to copy a line from what I'm doing, you can return back to this copy and paste it into your local copy. Does that make sense? Okay. Does everybody have a local copy of this document? Cool beans. All right. right, and a little disclaimer that this is modified from Geeks for Geeks. I did not come up with this all on my own. I just took something and changed it for our purposes. So let's go ahead and get started. And like I said, please raise your hand or just shout out, if you're behind on any part, because I want everybody to come out here with working code. All right, so let's get to coding. So if we click on this import required modules and then click the code block, it will put a code block under this. And so it says import. So what we need to do in Python is import everything that we're going to use. So we're going to use OpenCV, and then we're going to use a few things that Google Colab offers us as well. So the first one that you're going to want to do to import OpenCV is type import CV2, and that's OpenCV. And then CV2 or OpenCV has a method called imshow. And if you're on your local computer, it would show up with a pop-up window of whatever image you want to show. But Google Colab does not like pop-ups, so we're going to import a patch that Google Colab uses. So from Google Colab.patches, import CV2 _ imshow. And then we also want to be able to upload our shape file. So we are going to import something else from Google Colab. So from Google Colab, import files. And this will allow us to upload a file that is an image that we can use. So if we go ahead and run this by clicking this little play button, this green check says, yay, everything worked. So now we don't have to run this block again. Everything's going to stay imported no matter what code we add towards the bottom. So did that not work for anybody? Okay, cool. All right, now we need to upload and display whatever image we're going to detect shapes on. So I'm going to click on this and then code. And so this is a method from the files module. And the method is called upload. So we'll do files.upload. And I want to save this because whatever we upload, I'll save it in the variable uploaded so that we can reference the image and we can show it. But we also are going to need the file name in order to read in the image. So we'll say file name equals next iter and then uploaded. Because so uploaded is our complete, it has not only the file we uploaded, but it also has a bunch of metadata with it. And so the first part of the metadata is going to be the name. And that's really what we're after, is the name. So now let's go ahead and read in an image. And this hash or pound sign is a comment. So that's not code, that's just a comment if you're not familiar with Python. So if we want to read in the image, we'll read it into a variable called img, and we'll use OpenCV's imread module. And we'll read in the file name that we'll get from our upload. And then the last thing we want to do is we want to make sure it uploaded correctly. So we'll show the image. And here we're going to use that Google Colab patch. So it'll be CV2 _ imshow, and then the name of whatever we want to show, which is an image. So img. And so before you click run on this, go to Google or your browser, and you can say I don't know, OpenCV image or shape detection. And it should have some, and if you go to image, it should have some images of different shapes. You can do whatever one you want, but just download one and save it. I would recommend something like this would be really good, but just click on something simple. This is a harder example, and we'll see why later in the demo, but this would be good. So go ahead and save that image. And then if we go back here and we click run, down here it shows up with this choose files. So I'm going to click choose files. And I saved mine in pictures, and I called it shapes. And mine might look a little bit different from yours, but as long as they're shapes, we should be okay. So it loaded it in, and this is what my shapes image looks like. So we are all ready to go with an image to detect shapes on. Did that not work for anybody? You got an error? And you can also check what files are uploaded. If you go to this file button on the left, you should see whatever the name of your image was. And so that'll stay there as long as you're active on this document. When you close out, you'll have to reload it. But did it work for you, or is it still? Okay, cool, awesome. Okay, so now we're going to convert this image to grayscale. And we're doing this because it'll make thresholding easier, because we don't need to find a threshold for 3 different values, the RGB. We just need to set a threshold for 1 value. And so to do this, we'll add a code block, and we'll use a function from OpenCV. So what we're doing here is we're converting image to grayscale. And so we'll name it gray. And the function that's going to help us do this is cv2.convertColor. And what this function takes is it takes an image as input. So we'll give it img, which is our full color image that we just loaded in. And then it's going to want to know what we want to convert the color from and what we want to convert the color to. So we'll do cv2 dot, and then capitals are important here. Color underscore BGR, the number 2, and then gray. And it should autocomplete, hopefully, so you can just tab if you're unsure if you typed it right. But that's going to convert it to gray. So let's go ahead and show the gray image. So we can do that if we do cv2, our friend imshow. And then this time, instead of image, we're going to pass it gray, because we saved our gray image in a different variable. So you can go ahead and run this block, and it should come up with something that looks like this, or if you have different colors, it might look a little bit different. But did that work for everybody? Cool. Moving right along. Okay, so our next thing, I mentioned that we converted it to grayscale so that we can threshold it easier. So we're going to threshold the image. So if you type on your code block, we're going to use the function I introduced earlier, cv2.threshold. So here we are setting a threshold and getting a thresholded image. So we'll use cv2.threshold, and this is going to take the different arguments that I discussed. So first it takes an image, so we'll give it our gray image. Then it's going to take what our threshold is. And so because I've prepared this presentation, I know that a good threshold value is 127, and that's out of 255. So if anything's really dark or like really light, then we should be able to separate those. If you need to adjust it a little bit for your image, or maybe it doesn't pick up on all of the shapes, that's totally fine. But then our maximum value that we're going to set it to is 255, and we'll go with cv2.thresh binary. We're not getting fancy. I just want a black and white image with the shapes, 1 color, and the background, the rest. So let's go ahead and display the threshold. So we'll say cv2_imshow. And now, oh, I didn't return it. So this threshold's an image, but I didn't save it anywhere, so we can't use it. So threshold returns a 2 different values. The first one we don't really care about, so it's common practice in Python to just do an underscore. And then you can do a comma space, and we'll call our thresholded image threshold. So then if you run this, oh, I didn't give it anything to show. So I want it to show the threshold. So now all the shapes are black and the background's white. If you ended up with white shapes and a black background, that is a-okay. It doesn't matter either way, as long as the shapes are one color and the background's a different color. Does anybody's thresholded image not have at least one shape with two different colors of the shapes in the backgrounds? Okay, let me know if there's any issues. We'll work through them. Now we're going to get into the fun part. So we're going to find the contours of the thresholded image and draw them on the original image. So we'll do another block of code. And so we want to use the find contours method that I previously talked about. So cv2.find contours. And we want to give it the thresholded image called threshold. And then we need to specify how it's going to find these contours. And then when I was talking about the chain approx simple and the chain approx none, so we need to give it those two things. So how we're going to find it, we don't really care about the hierarchy, but I'm just going to do it anyways. So we'll say cv2.retr_tree. So this is going to return all of the hierarchies. So if you want to do something with that in the future, you have them, but we're not going to worry about that. And then for our method of saving the points on the contour, we'll do our chain approx simple. And so we need to assign some values to this. And so I said in the presentation that it returns two things, one of which is a list of the contours, and the other one is the hierarchy. But we don't really need the hierarchy unless you want to like print it out and show what it looks like. So you can either call it hierarchy or you can just use that underscore. So now we want to draw each of our contours. So we have a list of all of our contours, so we're going to iterate through that list. We're going to do that using a for loop. So for loops in Python look something like this. So we can say for contour in contours. So this is a new variable name for each of the contours that we're iterating through. But this is what's really important because it needs to match up here so that we have an object to iterate through, or a list to iterate through. So now using the draw contours, we're going to draw contours. So we can do that by saying cv2.draw contours. And we'll draw them on our original colored image. So you can say img, and then we want to give it one of the contours, singular, give it a single contour. And then the rest of it is just specifying different like lengths or different like widths and the color of the contours. So just kind of copy what I do here, or you can look up your own color. This 0, if I'm being honest, I don't really remember what that stands for, but the next one is going to be BGR values of what color we want our contours to be. So mine's going to be orange. I do not know this by heart. I looked it up before. So the red is 255 and the green is 165 to produce orange. And then we're going to save it in a width of 2, or draw our contours on in a width of 2. So now let's go ahead and show our contours. So we can use, again, our good friend imshow, and we can show the original image. And so when I click run, you'll notice that now it has these orange lines that are showing me the outline of each of the shape. And you might be saying, like, why does it do this multiple times? Well, that's because of my indentation. So this for loop, this imshow is still inside of the for loop. So I'm going to go ahead and backspace this. So I only want it to show the contours when it's done. You might also be asking, why is the whole picture outlined in orange? And that's because the first contour always is going to be the border of whatever image that you give it. So we'll ignore this when we're detecting shapes, but that's why that's there. Did that not work for anybody? Yeah.
Why is it being placed in the loop?
In the loop? Because we want to draw all of the contours on individually. I mean, I think because we put this in a list, you could probably do it all at once. But it's also good to just show like each contour being drawn on individually, or if you wanted to do like an animation. So you're 100% right. You could do it not in the list, but I just like to do it for the sake of iterating through, and we can tell when exactly each contour is being added.
And if it wasn't in the list, it would draw it like shape by shape.
So it's drawing it shape by shape because we are in a list, I believe. But yeah, that's a really good question, and you can take it out of the for loop and then see what it does for yourself as well. But now we're getting down into our final goal, which is to draw these contours or use these drawn contours in order to describe what the shape is. So this is going to be the majority of our code. So if we get a code block going, I mentioned that the first contour is that box. So again, we're going to iterate through our contours. So for contour in contours. But I don't want that first contour to be picked up because there's no sense in labeling a square image that's not really a rectangle in the image. So I'm going to create a variable, just an I, and set it equal to 0. And so I'll say if that I is equal to 0, then we don't want to do anything. We don't want to do whatever's in this for loop. We just want to go to the next iteration. So we'll set I equals 1, so we don't enter this condition again. And then we'll say continue. Oh, not contours. So all this is going to allow us to do is make sure that we're not trying to detect what the boundary of this image is, because it would obviously be a rectangle every time. So I want you to make sure that your cursor is now lined up with the outside of this if, because if it's inside the if, it will only do whatever we type for the first contour, and that's the opposite of what we want to do. If you want, you could type in else to be safe, and just write the rest of our code like this, but I'm just going to do it outside of the if. Okay, so I mentioned that we will be using our approx poly dp in order to estimate the different points. So that function is cv2.approx poly dp, and it takes a contour as the first one. So this, in this case, is why we're iterating through contours, is because we want to approximate it for each shape. And the second value I told you was a little weird. It's epsilon. It's our how far the approximation can be from the actual shape. And so you're about to see some strange math, but I will explain it in a second. So we'll do 0.01 times cv2 dot arc length, and make sure you capitalize the L. And we'll say contour and true. And then there's one final argument that we're just going to set to true, but I'm not going to go over this argument. I'll just focus on, or this argument is the closed or not, and all of our shapes are closed, so that's why it's true. But here this arc length, it's just saying that we don't want it to go outside of a 1% ratio of like the perimeters. So you can think of 0.01 as 1%, which is kind of like our error that we're allowing. And this arc length, it just gets the perimeter of the contour. And this true is also because our shape is closed. So are there any questions on that? Okay. We will move on then. All right. So we're gonna do some more things. The first thing that I want to do is I want to find the center of the shape, because I want to put our label of what the shape is in the center. And I will preface this with this is code that you can just Google, right? I don't want you to read too much into this because this is not the point. We're not trying to find the center of shapes, we're trying to label shapes. But how we do this is we can use the moments the moments function in the OpenCV module. So cv2.moments, and we can give it our contour. And so moments returns a bunch of metadata about our contour. And it's saved in a bunch of weird variables. So M is really a list that saves a bunch of information about our contours. And so this first thing, and you're going to see some kind of weird text here. So we'll go if capital M is M of M00 is not equal to 0. So this is just a gut check that, hey, we actually saved something in this list. Like we're not working with something that did not properly save from our contour. But the important part is the X and Y coordinates that represent the center. So our X is going to be saved in M of, and these ones make a little bit more sense because it's M of 1, 0. So 1 being X, 0 being Y. M of 1, 0 divided by M of 0, 0. So M of 0, 0 is just like our scale, like for the shape. But M10 will get our X coordinate. And so if we go Y, we'll do the same thing, but we'll do it with M01 because we want Y instead of X. So we can repeat this. And I want to typecast these to make sure that they're integers. So you can do this by enclosing this second part with 2 parentheses and just saying int or integer. All right, so now that we have the center of our shapes, now we get to do the actual thing, detecting shapes. So we'll say if the length of our approx, which is what we saved from the approx dp, or it should be. So we'll go up here and we'll save this as approx. And so those are our list of approximations of important points. So if this length is equal to 3, then we want to say that it's a triangle because a triangle has 3 points and also 3 sides. So cv2.putText, and then we can take our original image and we can say that we want to label it as a triangle. And the position of it is going to be offset 20 from the center so that we have room for this triangle text. And then the Y coordinate, that was our center. X and Y are saved here. And the rest of this is cosmetic stuff. So we want to make sure that it's in a font that's readable. So cv2.font_Hershey simplex is a good one. We'll go with that. And so the rest of it, like I said, please just copy this down. It's merely cosmetic. You can look at different fonts or different sizes. We'll give it a size of 0.5. We'll give it the color of white. So 255, 255, 255. And then we'll make it have a width of 2. So that's what's going to tell us if it's a triangle. Now, I don't want to type out all of this again because all that's going to change is this 3 and triangle. So I will go ahead and copy all of this, and I'm just going to paste it like a lot of times. And make sure that your indentation is not screwed up. So because Python, what it'll do is it'll go by indentation for its ifs. So if you have something that doesn't line up like this, it's going to go into this case at the wrong time, and it will never actually find anything. So like I said, all we're going to change is the numbers. So we'll go with 4, and 4 is a rectangle. And then we'll go with 5. 5 is a pentagon. And then we'll just go up to hexagon for time's sake. And this should all be not if, but else if. And so how that's written in Python is elif. So add an EL, in front of all of these ifs because a shape, if it's a triangle, it's not a rectangle. So we don't want it falling into both of those cases. And then our base case for what if it's none of these, we're just going to assume it has too many sides, so it's a circle. So we'll say else, and then we can put this same text and we'll just change it to circle. All right. Let's see. Now, all we have to do is just show our image. So make sure you're all the way to the left with your cursor because we want to show our image just at the very end after we go through the for loop and we look at all of the shapes and we label all of them. So we'll go cv2_imshow, and then we put all of these on our original image, img, so we'll put img here. All right, and then I'm going to run this. And with any luck, you will have a picture where it says triangle, circle, hexagon, rectangle. Does anybody's image not have any labels? If it doesn't, I'm more than willing to help you out afterwards, but I realize that it's close to 4 o'clock. So I included a little challenge here at the bottom that I'll just show you what happens. So the challenge is to run the same script, but maybe with an image where the shapes are not as clear cut. So I already did this. I used this image, which some of you may have seen on Google. And there's a lot more going on. And so when we threshold it, we see that it doesn't look very nice. Like this should be all white, this should be all white. So we might get sort of a bad result. So how we fix that is we use this blur. So blurring is another image processing technique. So if we use this blur function, we go from a thresholded image that looks like this to a thresholded image that looks much, much cleaner. Because without this, our detection is not going to be good. Let me show you what our detection looks like if we don't blur it. If we don't blur it, it's kind of all over the place. It doesn't know what to do. So that's why thresholding is really important for this task, because of that fact of it's going to directly impact how many contours it picks up on. So that is a bit of a harder problem. So if you want to do this with like real life images or anything like that, or anything a little bit more busy or complicated, go ahead and check out blurring. But we will go ahead and wrap up. So I'm going to just give you a very quick overview of what's next. So if you want to continue this project, like I said, you can improve the smoothing. You can do it with different images. You can just mess around and see what the functions are doing and what you can change to make it the best detection possible. And then also, if you use your laptop or your desktop's camera, this same code, as long as you save clips of a video as images, which if you go to OpenCV and you look at how to capture video, you can save video as images, and then you can use the same code on a live stream with your camera. So if you held up a square, like it would detect it and things like that. And then whatever other ideas you have, you can go next. I wanted to share with you some computer vision resources if you're interested in this. Personally, I love blog posts. So PyImageSearch, Towards Data Science, Medium, they're all blog post platforms where they have small projects and maybe even some more large scale projects that you can follow, and they have code for them. So you're not alone when you do this. Also, there's YouTube tutorials. There's a computer vision workshop that took place a year ago that was on our YouTube. And then also Geeks from Geeks, where I got the base of this code. And computer vision projects can be anything from a household object detector, so like a pen, to like a chair or something like that. And there's blog posts about that. You could detect color, which is what I did last year with Vanessa. And then you can also do like a motion detection and stuff like that with your own camera. But if you want to read up on your techniques before trying any more of these, I would suggest looking at blurring and denoising. Masking is also another technique that's capable with OpenCV. It's pretty easy. And then also filtering. So you'll look up words like kernel and things like that. And if you have any questions about this, feel free to ask me or just ping me on Discord anytime. I also wanted to give a plug at all of the computer vision going on at UTSA. So Rowdy Creators has a Tello drone project that uses computer vision. So if you liked this workshop, join their Discord server and try to get on that team. We have a course that's on deep learning that covers a little bit of computer vision, more advanced than image processing for sure. And then we even have a specific course for computer vision. There's also a lab on campus that does computer vision research called the Vision and Artificial Intelligence Lab. So if you're interested, maybe go look at some of their publications, look at the work they do, things like that. But that's really all I have. If there's any questions, please just feel free to stick around and ask me. I'll try to stick around at the end, but I just want to say thank you so much, and I hope y'all got working code to the text shapes. So thank you all.